Turning to slide 10, the outline shows that we are ready to talk about the measurement model analysis. So on slide 11, we have a measurement model that is a latent class analysis model. We have 6 indicators, 6 latent class indicators of the latent class variable C. In this talk, we're going to mostly focus on binary latent class indicators, where the influence from C to U is captured by class varying probabilities of U equals 1 versus U equals 0. That's parameterized in Mplus via thresholds. So a high threshold gives a low probability for U equals 1. We can also have ordinal variables where the influence of C onto U1, for instance, is captured by more than one threshold. So if you have 3 categories, you will have 2 thresholds. You can also have unordered variables, nominal variables, where the influence from C to U would be represented by means on the logit scale for that nominal variable. Or you can have continuous latent class indicators, where the influence from C is captured by class varying means of the continuous indicator. Or you can have count indicators, where the influence is captured by class varying means of the log rate for the count model. And you can mix all of those different possibilities in the set of latent class indicators. Now, class enumeration, deciding on the number of classes, is determined as part of this analysis of the measurement model. And for a more full discussion of LCAs, you can look at our short course videos, topic 5. So if something seems unfamiliar to you as I go through slides in the future here, just go back to short course topic 5 and refresh your memory on those topics. Slide 12 then shows a first input for Mplus, and the data file is called distal.dat. It is a simulated data set that I created, and is used for several different analyses in this Webtalk. The sample size is 1,000. And here is the list of the variables in the data set. And the variables that we're going to use for the analysis, the use variable, are U1 through U6, the latent class indicators. Missing data is flagged as 999, and we declare the indicators as categorical, meaning that they can be binary or ordinal as determined by the program. We're going to ask for 3 classes in our analysis. And we do a mixture type of analysis, which implies that we have the possibility of multiple maxima, and we want to choose many different random starting values, which are perturbations of the default starting values. So we have an initial set of starting values that are used for initial iterations, and then Mplus picks the 10 best of those for a full iteration to a solution. I use processors equal 8 or 12 on my computer, and you can see what choice is best for you on your computer in terms of speed of analysis. But using several processors is important when you have mixture modeling with many starts. And then I ask for technical output, the parameters that are free and fixed, etc. And Tech10 giving univariate and bivariate frequency table fits. And note here that no model command is needed, because we have the default of the thresholds or the probabilities of these binary items in this case varying across all classes by default. So that's the whole input for the measurement model. On slide 13, you have the output of Mplus showing the results of these random starts, ranked from best to the worst log likelihood values. So you have 10 of these here corresponding to the last 10 full iterations that we make. And you see that they're all the same. And here the likelihood is on the negative part, so a good likelihood is the likelihood that's as close as possible to 0. The unperturbed is rather the default starting values, and in this case actually we wouldn't have needed any random starts at all beyond that, but that's because the model is fairly well behaved, as it often is in simulated data. Slide 14 then gives you excerpts of the model fit information, 20 free parameters in this case, the log likelihood value for the model, we call it the H0 model, and the BIC value, the Bayesian information criterion, which we want a low value for. And we compare it then to having, say, 2 classes instead of the 3 we used, or 4 classes instead of the 3 we used. And at the bottom then you get the final class counts based on the estimated model for each of the classes, the number of people, and the proportions. So the class estimates of the class probabilities. In this case, the entropy is 0.68, so a moderately high value. Slide 15 then shows important output, 3 tables that come out in the Mplus output. The top table is not that informative. It's really an intermediate step to get to the second or middle table. And we discussed the transition from this table, the top table, to the middle table in the statistical methodology section. So that for now we're focusing on the middle table. And we looked at that before on slide 8 for the hypothetical data for 6 individuals. Here you have it for these real data individuals. And so the rows here represent the true latent class status, and the columns represent the most likely class being 1, most likely class being 2 or 3. So for instance, for people who are truly members of class 1, they have a probability of 0.864 to get a designation of most likely class of 1, that is the correct designation. But they also have a chance, lower probabilities, for being misclassified into most likely class 2, most likely class 3, whereas the true status was 1. So you have true status, true latent class variable, and then the observed fallible measurement error prone indicator of most likely class. Now, the bottom table we're going to discuss later, the logits here, which will be used for 3-step analysis, one of the 3 multi-step procedures. On slide 16 there, we have a table that I presented in a way that I like to use to interpret my solution. So you have a 3-class solution here, 3 classes, and you have the 6 latent class indicators. And here in the table are the probabilities for u equals 1 as opposed to u equals 0. So for class 1, you see then that you have high probabilities for all 6 latent class indicators. Class 2, you're high only on the last 3, low on the first 3. And for class 3, you're low on all 6. So let's take a closer look at how these indicators define these 3 classes. It's good to understand that, for instance, in terms of measurement instrument development. So I'm claiming here that U1 through U3 are key for defining class 1, because they are the only indicators with high probability for only class 1. You know, these variables, these indicators, have high probabilities only in class 1, not in class 2 or 3. Whereas U4 through U6, they're high also on class 2. So the first 3 are key for defining class 1. U4 through U6, the last 3, they're key for defining class 3, is what I claim. Not class 2, but class 3. What do I mean by that? Well, those last 3 indicators are the only ones differentiating between class 2 and class 3. So the first 3 items, they don't differentiate between class 2 and class 3. They have low probabilities for both classes. But the last 3 items, last 3 indicators, are high only for class 2 and low for class 3. So they are key for defining class 3. You can want to think about that. Now all of these 6 indicators are needed to define class 2, where the first ones are low and the last ones are high. That's the only class that has that feature, and you need all 6 to define it. Now you can look at that in more detail. The second sub-bullet here, the p-value sub-bullet, which shows up on the next slide, where the small p-values on the next slide for class 1, that's testing the difference in probabilities across classes, where you have small p-values, significant difference, class 1 versus the other 2, so class 1 versus the other 2. And likewise, to define class 3, you have small p-values for class 3 versus the other 2. So this is a little bit more involved. Slide 17 is actually a new feature in version 9. So it has to do with latent class indicator discrimination between classes. How well does an indicator discriminate between classes? You want to know that. So we do a quality test of probabilities across the latent classes. So here on the left you have the first 3 indicators, on the right you have the last 3 indicators. And here then you see the low p-value 0 here for class 1 compared to the other 2 classes. There's 0. Same thing for U2, class 1 versus 2, class 1 versus 3, both of those 0. Whereas for U4 through U6, it's actually class 3 versus the other 2, classes 1 versus 3, 2 versus 3, they are 0 here, showing that they're the ones that discriminate class 3 from the other 2. Just like we said here, U4 through U6, key for defining class 3. So those are 2 slides that can benefit from thinking through how this works out. So classes that indicators discriminate well between have low p-values, and discriminate poorly between give high p-values.